Hey, AP Chemistry, welcome to Intermolecular Forces. We're going to start talking about this today. So before we start talking about it, let me kind of give you a framework. First of all, when we talk about intermolecular forces, we talk about this chapter directly following bonding because it's kind of a form of like a pseudo bond. An intermolecular force is a force of attraction between two things, just like an ionic bond, a covalent bond, a metallic bond, etc. are all of those bonds are a force of attraction between two things, right? The difference is what those two things are. And so that's why I say that an intermolecular force is like a pseudo bond. It's a force, just like a bond, and it's based on the same thing. It's based on all of those considerations of Coulomb's attraction. So if you go back and look at Coulomb's law, that law really is going to govern intermolecular forces just like it governs all of the bonding. The other thing that I want to kind of wrap your brain around before we kind of get into the details is the effects of intermolecular forces. So intermolecular forces is this really big topic because it drives a lot that happens in chemistry. And one of the things that it drives is the formation or the transitions between all of the phases. So what is a solid and when does it turn into a liquid? And what's a liquid and when does it turn into a gas? And what are the transitions that happen between these things? All of those are governed by intermolecular forces. And so we're going to talk a little bit about liquids and solids in this chapter. And if it ever seems like it's coming out of the blue, like it's just random facts about liquids and solids, I want you to pause and remember that intermolecular forces are the driving force between all of these phase changes and even some of the structures that are formed when solids form. Okay, so it's all interconnected. We're going to talk about it all within one big group. It's all in one chapter in your book. And so let's get started, shall we? Okay, so before we get into the nitty-gritty here, let's take a minute and return to this chart. So we have talked about the differences between solids, liquids, and gases for a really long time, probably as soon as you started talking about science in middle school, maybe even elementary school, you start talking about shape, volume, ability to flow, compressibility. We talk about all of these things from solids, liquids, and gases. So what I want to do is revisit this chart and then tie it into an intermolecular force. So let's define what an intermolecular force is and then go from there. So we talked about how a bond is a force of attraction governed by Coulomb's law. So remember, Coulomb's law is talking about how the force of attraction is proportional to both the charge, the nuclear force, the atomic charge, right? The number of protons. And it's indirectly related to distance, actually the square of distance. So as protons increase or as nuclear force increase, the force of attraction increases. And we can see this in things like if we compare, let's pull up a periodic table here real fast. Okay, so if we compare a couple things that are similar, like sodium and magnesium, right? Sodium and magnesium, they're fairly similar atoms. They're fairly similar sizes. They have the same amount of energy levels. They almost have the same amount of electrons. Magnesium has one more proton, and so it affects the nuclear charge. It affects the charge that form. If we compare sodium and a bond with chlorine to magnesium and a bond with chlorine, we see Coulomb's law in effect here, right? We see that magnesium is going to be a 2+ charge attracted to chlorine's 1-. Sodium is going to be a plus charge attracted to chlorine's 1- charge. So because magnesium has a greater charge or a greater Z effective, more protons, it's going to have a greater force of attraction. So which of these bonds is going to be stronger? The magnesium-chlorine one is going to be stronger. We can also see that force of attraction is inversely proportional to distance. So we can do something similar, but instead of comparing sodium, that's not what I meant to do, with magnesium, let's compare sodium with potassium here. Okay, so sodium versus potassium, and let's again form a bond with chlorine. So if we look at sodium chlorine versus potassium chlorine, so sodium is actually, for being element 11, it's a pretty big atom. It has 3 energy levels, right? Potassium is going to have 4 energy levels, or potassium is going to have electrons in those 4 energy levels. So sodium 1, 2, 3, potassium 1, 2, 3, 4. So just because sodium is a smaller atom with a similar amount of Z effective, the sodium chlorine bond is going to be stronger than the potassium chlorine bond. Sodium is a smaller atom, and distance is inversely proportional to force. So as distance increases, force decreases, and actually it's distance squared. So distance is going to have a greater impact on that force of attraction than Z effective. Z, the nuclear force, is going to be a linear relationship and a direct linear relationship. Distance in force is going to be an indirect exponential relationship. Okay, so we have these forces going on inside of our bonds. And we've talked about the forces of bonds before, right? And we've talked about how the type of bond that is formed is going to be determined by electronegativity difference. So something with very similar electronegativity differences, like carbon and hydrogen, tend to be a polar covalent bond. Something with no electronegativity difference, like hydrogen, is going to be a non-polar covalent bond. Something with an extreme difference in electronegativity, like fluorine and hydrogen, that's going to tend, maybe that's a bad example. Let me take that example back. Let's do sodium and fluorine. That's going to tend to be an ionic bond. So we've talked about how this difference in electronegativity drives the type of bonding that occurs, and that has implications on the types of solids and the properties of those solids. Okay, so all of these forces that we just recapped, that we've been talking about for a couple chapters, they're all between atoms. Atoms attracted to other atoms. There's a force of attraction between those atoms, and that force of attraction is what we call a bond. Okay, now we're going to kind of shift here and talk about forces of attraction again. But these forces of attraction that we're going to talk about are not inside a molecule. They are between molecules. So if I have 2 water molecules, and these 2 water molecules both have dipoles, right? The oxygen end of the molecule is going to be partially negative. The hydrogen part of the molecule is going to end up being partially positive. And I have dipoles that occur on both of these, partially negative, partially positive. Well, the partially negative end of one molecule is going to be, I just drew that backwards. Come on. Here we go. Let's try this again. Oxygen end will be partially negative. Hydrogen end will be partially positive. All right. So the partially negative end of this molecule is going to be attracted to the partially positive end of a different molecule. And this force of attraction between two different molecules is what we call an intermolecular force. So you see this term, inter, and that means between two different things. So if we have intercollegiate athletics, that's where one college is playing against another college. And that is different than intramural sports, where there's groups that play against each other within one college, right? So bonding would be intramolecular forces, or forces inside of a molecule. What we're talking about in this unit is intermolecular forces, or forces between two separate molecules. And like we said, these forces drive things also. They can actually drive certain types of solids to form and not form. And we can talk about the properties that those solids get. These forces are going to determine whether something exists as a solid, liquid, or gas at room temperature, at STP, right? So they decide states, they decide properties. They have all kinds of implications like solubility and reactivity. Okay, so we're going to explore intermolecular forces here in this unit. All right, so let's read, now that we have defined intermolecular forces, let's revisit this chart and talk about all of these properties of solids, liquids, and gases and how they are driven by intermolecular forces. So this would be a good point in time to actually pause the video and try to fill out this form as much as possible. Think through it yourself. And see how much you actually do know about these topics before we just go out and fill it in together. Okay, so pause here. Let's do that. All right, I'm going to start with the easy ones, the ones that we've talked about before, right? So a solid is going to have definite shape, definite volume. If you pour salt out of a salt shaker, it's going to have a definite shape, and it's going to fill up a teaspoon, probably the same every single time, right? A liquid is going to have a variable shape. Liquids take the shape of the container that they're in, but they are going to have a definite volume, right? So liquids in your kitchen, you pour water into a measuring cup, it's going to fill up the measuring cup the same every time. Now, I am going to put this in quotes because technically liquids are compressible, and we'll talk about that in just a second. Okay, gases are going to have a variable shape. They also are going to fill whatever container you put them in and take on the shape of the container. They're also going to have a variable volume, and this we saw very clearly in the gases chapter when we talked about PV equals nRT. We saw that there's a whole bunch of factors we can change, and those factors can end up changing the volume, right? If we change the pressure, the volume changes. If we change the temperature, the volume changes. Of course, amount of moles is going to change that. Same for solids and liquids, though. But there's a whole host of other properties that we can use to change the volume of a gas. And this brings us to this idea of compressibility. So solids really, when you look at a solid, the actual particles of the atom, the protons, neutrons, and electrons, they take up most of the volume of a solid. Probably somewhere around 90% of a solid is going to be taken up by the subatomic particles. And only about 10% of a solid is going to be taken up by space. And so it's really, really difficult to take those atoms in a solid and push them closer together. So we say that a solid is not compressible. Liquids, on the other hand, they are compressible. A pretty good majority of the volume of a liquid is going to be space, and we can push those molecules closer together, squeeze in on that space, and change the volume of a liquid. Now, this comes with a caveat. You can't really do that inside my classroom. If we're sitting inside our chemistry lab, we're not going to be able to compress a liquid. But if you got better lab equipment, maybe at the entry chemistry level of lab equipment for college, then yeah, you can compress a liquid. And actually, as you change these same variables of pressure and temperature for a liquid, liquids also expand and contract slightly as well. And they expand and contract to a measurable amount. So we're going to say that liquids volume is definite. And they are compressible, but it's really hard to do. Okay, gases, yes, with an exclamation mark. We can actually do this. You can do this at home, right? You can take a balloon, stick it in your freezer. You have just compressed the gas inside your balloon. It's not a difficult thing to do. There's a whole bunch of ways that you can figure out how to compress a gas. Easily compressible. Rate of diffusion. So remember, diffusion is the rate in which the particles are going to move and mix with other particles. Remember that everything in the universe has a tendency towards greater disorder. And so these particles are just going to mix all by themselves until they have achieved that lowest energy state of the most disorder they possibly can achieve. And so they're going to mix all by themselves, but not solids. Okay, this is not applicable to solids. Solids don't diffuse. They are locked in place to each other, and they're not going to diffuse. Liquids, on the other hand, are going to diffuse, but their rate is going to be fairly slow. So liquid molecules are going to be moving slower than gas molecules. Gas molecules are going to have a very fast randomized movement. And so because liquids are moving slower, the molecules are moving slower, they still have some attraction to each other. So as they move past each other, they're going to influence each other's behavior. The rate of diffusion is going to be slower. Gases, that rate of diffusion is going to be much faster. Okay, ability to flow. So any body of fluid is going to have an ability to flow. So again, this does not apply to solids. Solids have no ability to flow. Liquids, on the other hand, they do have the ability to flow. They are considered fluid. 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 I don't know why that turned into an E in there. Let me fix that. Gases are also fluid. So gases can be considered bodies that can flow past each other. If you've ever talked about convection currents, you're talking about big bodies of gases that are rising or falling based on temperature and also based on density. Okay, so intermolecular forces now. Now that we have filled out this chart, again, this chart should look very familiar. You've probably filled it out in numerous high school science classes, probably your middle school science classes. You've probably even touched on it in some elementary science classes. And so we're going to take this the next step and talk about how this links to intermolecular forces. Again, it's really good to have a prediction down before we start talking about it. So if you want to pause the video here and make a prediction What is going to be the strength of intermolecular forces between particles in a solid, particles in a liquid, and particles in a gas? And then we'll talk through it together. So what we're really talking about is intermolecular force strength. And then remember, this is going to be the strength between molecules in a solid, liquid, and gas. Now, you can think of the same molecule for all of these. So if we want to talk about water, water is going to be our go-to, you may have noticed. Okay, so here's one water molecule, here's another water molecule. And we can talk about this in terms of solids, liquids, and gases for water. So solid water would be ice, right? Liquid water is just going to be normal water. And then gaseous water is going to be water vapor, right? So what's going to be the strength of intermolecular forces between water molecules in ice, water molecules in liquid, and water molecules in a gas? So the intermolecular force between water molecules in a solid in ice is going to be fairly strong. Notice that ice becomes very hard. Okay, it has a definite volume, it has a definite shape. It's not going to move, it's not going to flow, it's not going to be compressible. And that's because the intermolecular forces between those two water molecules is really, really strong. Now, there is a temperature component here, right? Those molecules have been slowed down. The temperature is below 0 degrees Celsius, and those molecules have slowed down enough for the intermolecular force that's between them to really take over and determine the form of the water, right? So it has really strong intermolecular forces. It's going to hold these water molecules at a very specific distance from each other. It's going to hold these water molecules at a very specific angle to each other, and we get a very specific crystal. If you look at ice crystals, and when they have enough time to form, they form very consistent crystals. If you look at like silicon dioxide crystals, right? They form very specific crystals. If you look at diamonds, they form very specific crystals with specific lengths in between the components and specific angles to each other. And that is what defines a solid. Strong intermolecular forces that have very definite lengths and angles to one another. Liquids do have some movement. So the molecules are moving a little bit. They are still attracted to each other, like we talked about, as the liquid particles flow over each other. They're still in like semi-contact with each other. They're not locked into place like a solid would be, but they're still influencing each other's movement. So liquids are going to have intermolecular forces between them. They're going to have, I'm going to say medium, okay, not as strong as a solid, right? But the intermolecular force is still there. Now gases, let's think about the state of a gas. Gas molecules are super far apart. And like we said before, like we talked about before, that force of attraction is guided by charge. I'm going to put a Q up here for charge, since we're not dealing with Z anymore. We're not dealing with the nuclear charge anymore. We're just kind of dealing with like partial charges that are caused by the dipole. So I'm going to put a Q up top and distance. So remember, force is indirectly related to distance. So the farther away molecules get, the weaker that force of attraction is going to be. Well, gas molecules are super far apart. They're so far apart that in our gas law chapter, remember, we talked about how ideal gases, we make the assumption in the kinetic molecular theory that ideal gases are so far apart that they don't influence each other at all. And that's why polar and nonpolar gases are still going to form homogeneous solutions with very consistent composition, because gas molecules are so far apart that their polarity doesn't affect each other, right? It's not like they're going to form layers of polar and nonpolar substance. They're too far apart to actually affect each other. Also, gas molecules are moving extremely fast past each other. If you think about holding somebody's hand, right? Holding somebody's hand is not going to work very well if you're running super fast in opposite directions. You're going to hold on, and then that's going to be broken apart, right? If you're going to hold someone's hand, you're going to stand still next to them so that you can hold their hand. You're not going to run in opposite directions as fast as you possibly can, because that's going to break the force that's holding you together, right? Okay, so gases, as a result, are going to have very few or a very low amount of intermolecular force attraction between them. Okay, there's our chart. It looks so pretty. It has so many colors on it. I love it. If you have questions on this, this is kind of like the intro to intermolecular forces. So we have kind of hashed out the concept of intermolecular forces for you. We have tied it to a couple contexts. If you have questions, now would be a great time to jot them down in your margin. And we'll kind of get into individual aspects of intermolecular forces from here. All right. So intermolecular forces is kind of a fun chapter because it relates to so much that we have already talked to. We've built all of these individual building blocks. We've talked about solutions. We've talked about thermodynamics. We've talked about gases. We've talked about solutions. We've talked about all of these individual building blocks. Well, now intermolecular forces comes in and kind of fills in the details to us. So one of those details that we need to kind of go back and look at is kinetic energy. So remember, this funny looking little E represents kinetic energy. Remember, this is the degree of motion of a molecule, and it's extremely dependent on temperature. In fact, you would say that temperature is the macroscopic observation of this microscopic idea of kinetic energies, right? The faster molecules move as they absorb energy, they move faster. And the faster that they move, the more they're going to bounce off each other, expand off each other. And then the little liquid, whether that's mercury or alcohol in your temperature, in your thermometer, is going to expand and rise. And we see the temperature rise on our thermometer. So kinetic energy and temperature really are expressions of each other. And kinetic energy keeps particles moving and apart. So kinetic energy works to break intermolecular forces. Intermolecular forces tend to draw particles together. And so the more kinetic energy you have, the more it overcomes intermolecular forces, and vice versa. The more intermolecular force you have, the more you're going to overcome kinetic energy. So kinetic energy and intermolecular forces really work against each other. They are expressions of opposite ends of our description. If you have something with very low intermolecular forces, those intermolecular forces may have been overcome with kinetic energy, and vice versa. And so these two things work to explain a lot of the phase changes that occur. They work to explain condensed phases like liquids and solids. These two tend to have stronger intermolecular forces. These two things, kinetic energy and intermolecular forces, work to explain phase changes. So if you increase the temperature, your thing tends to move from a solid to a liquid to a gas because intermolecular force is being overcome by kinetic energy. If you increase pressure on your substance, it tends to force gases to become liquids, to become solids, because you are forcing molecules closer together. and then intermolecular forces tend to take over. And so these two things work together to explain a lot about phases and phase changes. Intermolecular forces, when we compare them to bonds, they're generally weaker than ionic or covalent forces, right? It takes about, for example, if you're looking at hydrochloric acid, right? If we're looking at the intermolecular force between these, here's two hydrochloric molecules, right? We have dipoles for both of these. We're going to have attraction between these two molecules. The partially negative end of one will be attracted to the partially positive end of the other. Well, in order to break this intermolecular force between hydrochloric molecules, right? And so what that would look like is taking the hydrochloric acid and moving it from a liquid phase, breaking the intermolecular forces and turning it into a gaseous phase where they can move independently of another. It takes about 16 kilojoules per mole in order to do that. 16 kilojoules is all it takes to break the intermolecular force. If we were to look at breaking the polar covalent bond, it would take 431 kilojoules per mole in order to do that. So that is taking the hydrogen and ripping it off from the chlorine. It takes about 431 kilojoules per mole to separate that. So again, we see this idea that intermolecular forces generally tend to be much weaker than our polar covalent force, also true for ionic forces. Said another way, it takes less energy to go through a phase change than it does to go through a chemical change, right? Now, this is also true for phase changes. If we look at the phase change between a solid and a liquid, that would be melting. And the phase change between a liquid and the gas, that would be vaporization. Okay. The phase change between a solid and a liquid, what you're doing is you're taking these two molecules that are locked in to each other, and you're just slightly breaking them so that they can move around each other. You're not completely breaking that force between them. You're just slightly breaking it. You're just unlocking it so that there's some movement there. The energy required to do that is much less than the energy required to undergo a liquid to gas phase change. So liquid to gas, what you're doing is you're taking these molecules that can kind of move past each other, right? And you're completely separating them so they have no interaction with each other whatsoever. So it's going to take a lot more energy to completely separate these molecules from each other, so they have to completely break that intermolecular force, than it is to just partially separate them. So it takes less energy to undergo a solid to liquid phase change. It takes more energy to undergo a liquid to gas phase change. Okay, a couple other things that can reflect the intermolecular force, right? So we talked about how temperature is a reflection of kinetic energy. Well, we have a couple of these things that we can measure and look at macroscopically that are reflections of the microscopic intermolecular forces, and that would be melting and boiling point. All right, so boiling point is going to be the temperature, right? If I ask you what's the boiling point, you're going to tell me, oh, it's 100 degrees Celsius. You're going to tell me a temperature. So boiling point is the temperature, at which something occurs. And what is that something for boiling point? It's where a liquid turns into a vapor, right? So what's the boiling point of water? It's 100 degrees Celsius, because at 100 degrees Celsius, liquid water has enough energy to absorb to completely overcome the intermolecular forces between water molecules, separate completely, and become water vapor, right? That's what a boiling point is. So what is melting point? If you were to give a definition for melting point, what would it be? This would be a good time to pause the video and see if you can write that down. So a melting point, again, is going to be a temperature. It's the temperature at which something occurs. And that something is going to be melting, right? It's the phase change between solid and liquid. So what is the melting point of water? Well, it's the temperature at which solid water molecules can partially overcome the intermolecular forces between them and start to move around. And that happens for water at 0 degrees Celsius. So melting point is a temperature at which a solid becomes a liquid. For water, that's going to be 0 degrees Celsius. Now, that boiling point and melting point is going to be different depending on what you look at. If you look at carbon dioxide, for example, carbon dioxide has extremely different boiling points and melting points, right? Its melting point of carbon dioxide is like negative 70 degrees Celsius or something like that. Oh no, I think that's the boiling point. I don't know, but it's really cold. And that's a reflection of the intermolecular forces that are between carbon dioxide and carbon dioxide molecules versus water to water. So where we're going to go next is we're going to talk about the 3 types of intermolecular forces between molecules. Intermolecular forces between molecules are not equal, and water versus carbon dioxide is a really great example of this. If we think about a water molecule being attracted to another water molecule, right? Intermolecular forces between water molecules. Now, on the flip side, let's think about carbon dioxide. So we have carbon dioxide being attracted to another carbon dioxide molecule. Okay, so I want you to pause here and think, what's the difference? What is the difference going to be between the attraction between 2 water molecules versus the attraction between 2 carbon dioxide molecules? Pause the video here and see if you can jot down a couple differences between these 2. And this is going to lead us into our discussion of the 3 types. You can see that the attraction can't be the same, right? Water molecules have an overall dipole, where it's going to have a partially negative end of this molecule, and it's going to have a partially positive end to the molecule, and the partially negative end can be attracted to the partially positive end, and you get an intermolecular force. Carbon dioxide doesn't have this. Carbon dioxide does not have a net dipole on the molecule. It is a nonpolar molecule. There is no dipole. There is no partially positive end. There is no partially negative end. So what is actually doing the attraction between 2 carbon dioxide molecules? We know there has to be an attraction because carbon dioxide can take a solid form. If carbon dioxide can be solid, there must be intermolecular forces between them, right? But it's definitely not based off of a dipole. It's definitely not based off of electrostatic forces, even if those electrostatic forces are partial electrostatic forces. So what possibly could be there? So let's talk about it. There are 3 types of intermolecular forces that we generally see in molecules. Those 3 types are listed below, and we're going to go through all 3 types. So one would be an ion dipole intermolecular force. Another would be a dipole-dipole intermolecular force. And a third is called London dispersion forces or van der Waals forces. Now you'll see in here that hydrogen bonding is listed kind of as a subset. Hydrogen bonding, we'll talk about, is a type of dipole-dipole force. So if hydrogen bonding is occurring, it's a dipole-dipole force. It's just a special type of dipole-dipole force. Okay, so let's talk through these three types of forces. All right, the first is going to be an ion dipole force. So an ion dipole force is where you have an ion, like an anion, for example. Chlorine negative could be an example of this, or a cation, Na plus could be an example of this. So you have a true charge on one side, and that true charge is attracted to a dipole, like the dipole that occurs across a water molecule, for example. Okay, so notice in the first example with chlorine, with our anion, it's attracted to a positive, partially positive part of the polar molecule. In the opposite end, the cation is attracted to the partially negative part of the polar molecule. So if I gave you a water molecule, you should be able to draw for me where a chlorine would be attracted, a chlorine ion, and where a sodium ion would be attracted. Where would that chloride ion be attracted to on the water molecule? Where would the sodium ion be attracted to on that water molecule? Pause the video here, see if you can draw it in. Okay, a chloride ion is going to be attracted to the partially positive end of the molecule, which would be down here by the hydrogen. So the chlorine is going to be attracted to the partially positive end of the molecule. And then the sodium is going to be attracted to the partially negative. Because sodium is positive, it's going to be attracted to the partially negative end of the molecule, or the oxygen end of the molecule. So that would be an ion dipole attraction. It's not a true bond, right? It's a force of attraction between a complete charge and a partial charge. So this is going to be less strong than an attraction between two complete charges. And we would classify it as an intermolecular force. You can see here molecules being attracted to other molecules. I like this picture because it's three-dimensional, and this would be an example of a dipole-dipole attraction. So we have a water molecule and a water molecule. Both of these things have dipoles, right? And the dipole on one is going to be attracted to the dipole on the other. Now, this is going to tend to be less strong than an ion dipole, right? A partial charge attraction will tend to be less strong than a complete charge, partial charge attraction. Notice that both of these molecules are neutral. If I talk about water's not a charged molecule, right? It's a neutral molecule that contains a dipole inside it. So it's between neutral polar molecules. We talk about these molecules spending time near each other. They're not locked to each other. These forces are going to be dependent on Coulomb's law, where they will, as charge increases, the force increases. As distance increases, the force decreases. As the dipole moment gets stronger, the boiling point is going to be higher. So as the dipole moment gets stronger, you're going to need to input more energy in order to separate these molecules from each other. And therefore, you're going to have a higher boiling point. Okay, now there is... there's a couple trends that go along with dipole-dipole bonding. There's a couple caveats that we want to talk about, like hydrogen bonding. But just to round out our idea of intermolecular forces, I want to define van der Waals forces, or London dispersion forces, today. So London dispersion forces are going to be between nonpolar molecules. So this is the carbon dioxide attraction that we talked about. Again, because nonpolar molecules can exist as liquids and solids, right? Diatomic bromine is a liquid. Diatomic iodine is a solid. Carbon dioxide can be a solid. We can have liquid nitrogen. There must be intermolecular forces that are attracting these nonpolar molecules to each other. And what's going on here, we tend to call London dispersion forces or van der Waals forces. So what happens, you can see in this little diagram here, is this would be an example of helium, right? Helium is a nonpolar molecule that has 2 electrons that are flying around it, right? And as those electrons fly around it, once in a while, you're going to find those electrons shifted to one side. Well, if those electrons instantaneously shift to one side and create an instantaneous dipole, right? One side would be negative for just an instant. One side would be partially positive for just an instant. If this happens when the molecules are close to other molecules, they can influence that dipole that occurs in just one instant can influence the molecules next to it to also develop an instantaneous dipole moment. And if you get enough of these shiftings to occur all at the same time, you have temporary dipole moments that are now attracting each other and able to cause phase changes to occur. Now, obviously, this has to happen. This is not going to be a very stable force that's going to be attracting each other, first of all. Second of all, the molecules have to be really close together. So that has implications for temperature, has to be very low temperature, or pressure, has to be a very high pressure. So carbon dioxide is an excellent example of this. We see this happen with carbon dioxide when the temperature is very low, right? Solid carbon dioxide can exist at very low temperatures. Also, under pressure, if you take a little solid carbon dioxide or dry ice and you pressurize it, you can actually get that dry ice to form liquid at a room temperature under very high pressure. So it has implications for temperature and pressure. It also has implications for the size of the molecule. If you have more electrons, this is going to happen more easily. Those electrons will shift, and you get more electron shifting, you're going to get more of a dipole that can influence others around it. And so we talk about atoms that go through this in terms of their squashiness. And I swear I did not make that term up. That term is actually in your textbook. It makes me think of this picture right here. If a hippopotamus sat on a person, that person would be very squashy. And if there is more electron cloud to shift, the atom is said to be more squashy. It has a higher degree of squashiness. It's possibly my favorite word in all of your textbook. So this is why we're going to tend to see when we look down that halogen chain, right? We look down that halogen family. Notice that fluorine and chlorine at STP are gases, bromine's a liquid, iodine's a solid. And this is why, because as you get more electrons, iodine has the most electrons out of all of those, you're able to shift those electrons and form these instantaneous dipole moments much easier. So if you have things that are larger, you're going to be able to do this. If you have things that are less compact, you're also going to be able to do this more easily. So tomorrow we're going to come back and we'll talk through some of the particulars of all 3 types of these intermolecular forces. But at least for now, you have a definition of all 3 types, and we can kind of fill in details from here. Let me know what questions you have. I will see you in class.